Hi, I'm Tom Hayes, and my talk is titled Wake Up and Join Me, an energy-efficient algorithm for maximal matching in radio networks. This is joint work with Varsha Dani, Ayush Gupta, and Seth Petty. We're motivated by the problem of networks of low-cost sensors which communicate by short-range radio. And these may be deployed in remote and hazardous terrain where we don't know the topology of our network. Um, and Battery life or energy usage is the dominant cost we're interested in. Communication cost is the most important contribution to that. And additionally, as these devices get smaller and smaller, the cost of listening tends to be comparable to the cost of sending messages. So our model also reflects that. Specifically, our network is modeled by a graph on n nodes, each representing a processor. Our time is measured in discrete time steps, and at each step, a node can either sleep, send, or listen. Now, when you send or listen, it costs you a unit of energy. You can send up to log n bits at once. When you listen, you get a message if and only if exactly one of your neighbors is sending. If two or more of your neighbors are sending at the same time, their messages collide and you don't receive either one. And of course, if none of your neighbors send, then there's no message for you to receive. All the nodes in the network start out the same way, and the only information they have about the network topology is knowledge of an upper bound on the number of nodes, n, and on the maximum degree, delta. Now, our goal is to execute some network task, and we want the algorithm for it to run in polynomial time and to use only polylog energy per node. In this talk, we're going to be concerned with the maximal matchings problem, in which each node tries to find a partner from among its neighbors. And this pairing has to be a matching. It has to be one-to-one. Now, a matching is considered maximum if it contains as many matched nodes as possible. It's maximal if you can't add any additional edges to it without deleting some of the existing edges. So maximum is like a global optimum, and maximal is only a local optimum. But we have this fact that every maximal matching is within a factor 2 of the size of the maximum matching. So we're going to solve the maximal matching problem. Now, in a centralized setting, both of these problems are in polynomial time. For maximal matchings, there's an easy greedy algorithm, and maximum matchings can be solved by a number of algorithms based on augmenting paths, such as the Hungarian algorithm or Edmonds's Blossom algorithm. In the distributed context, the problem is a bit harder. I'm going to now give you the main idea of our algorithm. So suppose that we had a d-regular graph where we knew the degree d. To avoid collisions, most of the nodes will be asleep in any given time step, but a random 1 over the degree fraction of the nodes wake up and try to form edges. Now, when we wake up, if we're lucky, exactly one of our neighbors wakes up, and in that case, we can exchange IDs with that neighbor and agree to be partners. And once we've formed an edge like that, we drop out of the game. If we're unlucky, we wake up at the same time as either none or 2 or more of our neighbors, whose messages would interfere with each other. But fortunately, a constant fraction of the time when we wake up, exactly one of our neighbors will wake up and an edge can be formed. So that's pretty efficient. Now for a general graph, which is not a uniform degree, we can still try the same idea, which is that each vertex will wake up with the same probability R of t. R of t is just some function of the time step. And an edge will form whenever two adjacent nodes wake up, but none of their other neighbors wake up. So the idea now is start out with this participation rate being 1 over the number of nodes, which works well for high degree vertices. Eventually, all of the high degree vertices will either get paired up or the degree will reduce significantly because most of their neighbors will get paired up. At that point, it's not a high degree vertex anymore, it's a lower degree vertex. We can now gradually increase the participation rate R of t so that it stays about 1 over the maximum degree of the residual graph. And it turns out that this can be done on a fixed schedule where the participation rate depends only on the time step, and that will work for any graph. Additionally, in what I just said, really, instead of having nodes wake up or sleep on a per time step basis, we need to execute a 3 time step handshake protocol. That's to ensure that when edges are formed, both endpoints agree about whether the edge has been formed or not, despite the possibility of some messages colliding. So our main result is this theorem that there is a randomized distributed algorithm that finds a maximal matching in time linear in the maximum degree using only polylog energy per node. One application of this algorithm is that we can solve the neighborhood assignment function problem. So suppose that I want to back up each node in my network by sending its data to one of its neighbors to store a copy of. Well, I would naturally want to minimize the load on the nodes doing the backing up, which means that I should assign as few neighbors as possible to each of them. So this is the problem of getting a minimum load neighborhood assignment function. And we can actually find an approximately optimal map of this kind within a log factor using polylog energy and nearly linear time. And the idea behind it is to start with a maximal matching, use the edges there to back each other up, and then take those nodes out and work on the residual graph, find another maximal matching to try to back up as many of those nodes as possible. And repeat this until every node has been assigned. Finally, some open questions are to find time and energy efficient algorithms for other important network problems, such as routing, coloring, leader election, preference aggregation, and so on. We'd also like to increase the robustness of our sensor networks against things like node deletions, node insertions, possible timing desynchronization, and hacked nodes or Byzantine faults. So I'll stop my talk there. Thank you for your attention.